So we looked at h and k yesterday, and today we're looking at this a value. So take a look, we're graphing y equals a times x squared. Yesterday we saw x squared plus k, or x minus h squared, two different types of transformations, vertical shifts and horizontal shifts. Right? That's what we were doing yesterday. So I'm going to quickly graph the base function, -3, -2, -1, 0, 1, 2, 3. And we know, I hope now, that it works like this. Okay? And if I graph it, I'll graph this one in red. On the learning goal today, you had to graph this both times. And again, it's because we really benefit from seeing how we start with the base form of a quadratic, or the parent function we call it, and how adding a number in there somewhere, how it changes it, how does it transform it. That's the best way to think about this stuff. So what if I have y equals 3x squared? Well, I'm taking the x squareds and I'm multiplying by 3. So Liam, what happens? Not 36. What's 9 times 3? 27, right? It's going to be my x squared, which was 9, times 3. So my x squared, which is 4, times 3 is 12. 1 times 3 is 3. 0 times 3 is 0. It did not change the vertex. That's really important for helping us be good at graphing. 1 times 3 is still 3, positive 3, 12, 27. When you have an a value like that, often the last two numbers will go off the graph. So those 27s, I can't fit them on the graph. That's okay. You can always fit at least 5 though. I can't think of a time where you're going to be asked to graph and a whole bunch of points go off. It's really only those last two. Okay, so let me graph those. So I want to tell you something. So the vertex didn't change, but when I went to -1, instead of going up 1, I tripled that and went up to 3. That's a difference of 2, but I didn't add 2. So look at the difference, the vertical difference between that point and that point. The blue one directly above it. It didn't move side to side, it moved directly up. It's got a difference of 2. But I didn't add 2. I multiplied by 3. So the next point doesn't go here, right? I take my point, the red one, which was at 4 times 3, and it goes up to 12. So what this does is it takes my graph and it stretches it, because the small points only move a bit and the big points move a lot because I'm multiplying. 4 times 3 is a bigger difference than 1 times 3. So it's a stretch. And like I said, 27 goes off the graph, so I can't fit it. So then I'm going to come down. Try not to make it look like a V. And that's equation 2, which is, y equals 3x squared. What happens if I multiply by a half? I go back to my x squared, so I take 9. What do you think, Jaden? It's going to compress it. Very good. So I take my 9, and I cut it in half to 4.5. I take my 4, cut it in half to 2. I take my 1 and cut it in half to 0.5, or half, right? You could use fractions too, whatever works for you. 0 is still 0. 0 divided by 2, or 0 times a half is still 0. Still positive 0.5, positive 2, positive 4.5. So what will that look like? My vertex didn't move, but instead of going up 1, I only went up a half. Instead of going up to 4, I only go halfway. Instead of going up to 9, I only go halfway. For my base function, the second column there, what would it go to if I went out 4? Megan, how far would I go up? If I go out 4, so over 4, what would I go up? Or anybody? That's good. Anang? No? Oh, in the new one, in the base function. 16. right? 4 over 4 up 16, square it. Yeah. So if for this one, I go over 4, not up 16, but up 8. So I could put, like, you don't have to necessarily, because 7 points is a lot. But we know, like, I can just figure out what all the next points are. I'd go over 5, up 25, cut it in half to 12.5. Not necessarily useful. I'm not going to add those points, but you could, right? You can just come up with points on the spot. And there you go. There's graph 3. Y equals 1/2 x squared. So what do you think? So now we've seen what K does. It doesn't change the shape. There's no stretch. There's no compression. It just moves it up and down. Same shape. We've seen what H does. It moves it side to side, the opposite way of what you might expect. Right? Side to side does not change the shape. What does A do? A doesn't move the vertex around. Vertex stays in the same place. But from the vertex, it stretches everything or compresses everything down closer to it. Okay, last thing to look at here. We're going to do the same thing. -3, whoops, I don't want green. -3, -2, -1, 0, 1, 2, 3. This would be 9, 4, 1, 0, 1, 4, 9. What if I multiplied all of them by -1? This is negative x squared. What's it going to do, Rachel? Make them negative. So the first one's -9, -4, -1. Not -0, 0 is just 0. -1, -4, -9. So I'm not going to graph the first one. Well, actually I can. It would look like this. Okay, and then if I reflect it down, the points go here. And that's what we call it. We don't call it flipping, although that's what people like to call it, but we call it a reflection, the technical term. Because it looks like it's reflected in the x-axis. It's like a mirror image of the one pointing up, but now it's pointing down. And when does that happen? When the A value is negative. Does that make sense? So what if I made it -2? Well, it's going to be negative. It's going to be negative. And instead of 9, it'll be 9 times 2, which is 18. Instead of 4, 4 times 2, which is 8. Instead of 1, 1 times 2, which is 2. 0 doesn't move. And then -2, -8, -18. So for this one, I went over 1, down 2. Over 2, down 8. Over 3, down 18. It was negative, so instead of going up, we're going down. And I multiply. Actually, what we can do is you can go like this. Up 1, 4, 9. That's the base pattern. Multiply by -2. Down 2, 8, 18. And I can find my points. From the vertex, there's my vertex. Go over 1, down 2. Over 2, there's 4, but I go down to 8. Over 3, it's going to go off the graph, but I'm going to try anyway. Instead of 9, I go down to 15, 16, 17, 18, somewhere around here. And it stretched it and reflected it. What do you think? Now that's it. There's an H value, there's a K value, there's an A value. That's your quote-unquote y equals mx plus b. Done. That's everything. But we got to put it all together and be able to graph all different variations of changing all those numbers. Positives, negatives, big numbers, small numbers, fractions, whole numbers, everything. Right. Okay, so there's different kinds of answers to that. The first answer is the parabolas you see in math class, because this is just an introduction, may not seem like an applicable kind of thing. But we're just learning about math. Like, we're in here to learn about math, learn about relationships, stretch our brain, work our brain out, that kind of stuff. That being said, the parabola is actually, in some ways, maybe one of the most important shapes, like in our world, especially of technology. So if I throw something, look out that I don't hit you, like an eraser, it follows a parabolic path. So for example, if you're programming a video game, and these days video games are pretty realistic, and you're shooting a basketball in the video game or something, or any sport, the programmer would have to understand this, and they would have to understand the forces of the player, like the imaginary players in the video game, kicking that ball, shooting a gun. The bullets these days drop over time, right? Like if you are playing a shooter and you shoot a long way, the bullet has dropped. You have to account for that. So they would have these kinds of equations built into the code. If you have satellite TV or internet at home, satellite dishes are parabolic. Three-dimensionally parabolic, but parabolic. Or like the satellites in space have parabolic dishes on them to send and receive information. There's actually all kinds of uses that you would have in the real world. It's a really, really important shape. Okay. And we're going to do some word problems eventually, some applications, and you'll see some more examples of where that happens. Okay. So here we go. Again, you don't have to write this down. You can just watch, but like maybe give yourself a slap in the face, make sure you're still awake, something like that. What's the domain of this graph? Think about what this graph is. It has a shift down 3. It has a shift to the right. It's minus, so it goes the other way to the right 5. And it has a stretch, a vertical stretch, right? Because it's times 2. So the growth pattern is going to be multiplied by 2. What's the domain? Jaden, what's the domain? Yeah. Good. Domain doesn't change. What's the range? Is it opening up or opening down? Kristen, what do you think? Up. So it's going to go like this. Y is an element of the real numbers such that y is always greater than or equal to, and what number do I put in there? -3. The direction of opening is up. What's the vertex? Liam, do you know the vertex? This, Liam? Very nice. So +5, -3. I moved over to the right 5 from 0, 0, and down 3. So what's the axis of symmetry? Other Liam? Very good. Optimal value. Tara, what do you think? Max or min? Min, very good. There you go. Got it. And the transformations, I'm going to do this one. Okay, so there's no reflection. It has a vertical stretch by a factor of 2. It has a vertical shift down 3 and a horizontal shift right 5. So that's how you say the stretch one. A vertical stretch not by 2 or up to. It's not the same as a shift by a factor. That's an important part of it, turns out, by a factor of 2. Alan, yes, what were you going to ask?
How do you know if the stretching or decompressing is going to be horizontal or...
We don't do vertical stretches or compressions. Good question. We don't do them in grade 10. So there will be no, horizontal stretches and compressions. We don't do them. So you won't see them. You see them in grade 11.
What's the definition of a factor again?
A factor is like, it kind of means, has something to do with multiplying. So that's why we're not adding 2 every time. We're multiplying by 2 every time. So we say by a factor of 2. Okay, next one. What's going on in this one? It's got a horizontal shift to the right. It's got a vertical shift up. It's negative 1/2. The A value. So the A value is negative 1/2. H is 3 and K is 4. So it's shifting to the right 3. It's shifting up 4. It's got a reflection and a compression. Alan?
Doesn't it go down 4? This is the opposite.
No. Inside the brackets is opposite. Outside the brackets is not. Okay? So what's the domain? Sebastian, do you know what the domain is? What would be your guess? That's right. In other words, X can be anything. Parabolas are kind of always like that. Yep. Yes. Have you noticed that? Yeah. Parabolas are always like that. Okay. Y is an element of the real numbers such that Y is always... Does this one open up or down? Sure. Down. Very nice. So I'm going to answer that down, which means Y will always be less than or equal to what value? Jaden? 4. The vertex.
What is not a real number?
That's a big question. I'll answer that in a few minutes. Okay. The vertex is going to be, positive 3, positive 4, because I went to the right 3 and up 4. Axis of symmetry is X equals 3. It has a maximum of 4. And here we go. Here, this one's going to I have to write 4 things here. So this is how you write it. A reflection in the x-axis. A vertical compression by a factor of 2. Right? 2? Yes. Sometimes textbooks call that 1/2, so it would be fine to say 1/2 as well. Vertical shift up 4 and a horizontal shift right 3. Yes. Hold on, rip and read first. Right, but we're dividing. You could say half, but we're compressing by a factor of 2. So 2, which means we're dividing by 2 or multiplying by half. So you can say half, that's also allowed, but you can also say by a factor of 2 because it means you're compressing, which means you're dividing by 2. So you can say it either way. Jaden.
Would you use it as a fraction if A was negative 2/3?
It's still a compression because it's still a fraction. You probably won't really see that very much in this course. But yeah, basically that's still a compression. So if it was 4/3, it's bigger than 1, that would be a stretch. But it'd be a weird kind of a stretch, awkward. Yep.
Is it possible to compress by more than a factor of 2?
Absolutely. You could compress by anything. But imagine if you compressed by 15. All the points would be so, you couldn't really draw that by hand, right? Everything would be just too small. Okay, so here, I'm not going to go over this. This is just again, this will be online. It's a summary of everything. There's A times x minus h squared plus k. A is a reflection if it's negative, a compression if it's a fraction smaller than 1, and a stretch if it's a number bigger than 1. H is a horizontal translation or shift. K is a vertical translation or shift. A couple other little notes about how you find the vertex and that sort of thing. Any questions? Yes?
Would you ever have x the element of a real number, something different? Or would it always be the same with the vertex?
For domain, for parabolas, what we're working on now, it's always just x can be anything. There's never really a time where that doesn't happen. I think this is the wrong one. Okay, quick little demo here, if I can get this to work. So here's our base function. Look at the equation there, y equals x squared. A is 1, h is 0, k is 0. Okay, what happens if I move h? I move it all, whoops, something's wrong there, but I move everything to the left or to the right. What happens if I move k? I move it all down or move it all up. So what happens if I change a? Look at how all those points stretch up or compress, compress down. See, that's compressed, that's stretched. And then if I make a negative, it flips it down. And we can't really see it, but there it is. Or I can put a back to 1, and then I'm essentially not multiplying, and it just stays right there. Riley?
If a is 0, is it just a flat line?
Yeah, what I actually could do, is if I make a 0, this whole part is gone, so the whole x squared part's gone, so it's just a flat line at k. It's like y equals 10, right, is what it's saying. Does that make sense? Kinda. It's not something, like that's a good connection to make, but that's never really going to come up for us. That's something you need to worry about. Jaden?
And parabolas ever be sideways?
You can draw a shape that's sideways, and it would follow a parabolic path, but it's a totally different kind of graph for important reasons that we don't really get into in grade 10. So it's something very different. It would be hard to write it y equals something. You couldn't write it that way. You'd need to write it in a different way, so it's a different kind of thing. Okay, so again, I just want you to watch. How would I graph this quadratic relation? Before I do it, somebody tell me something about it. Y equals 2x squared minus 3. Madison, could you tell me anything about it? No? I'm good? Not right, because it's not in brackets. Where does the shift go? Not in brackets. Down, right. It's outside brackets at the very end, outside of the squared. So it's up or down. If I go back up to this, remember the h inside brackets is the horizontal. Does that make sense? Okay, good. So it's down 3. What else does it have? Okay. Very nice. It's vertically stretched. So I'm going to kind of draw it twice. You would do this, when you do it, you would do it all on the same grid. I'm going to do it on 2 grids. So I start with my main graph, and I know it really well by now because I've done it so many times, right? All of you have done this so many times. Okay, there it is. And every one of those points is going to be stretched by 2. So instead of here, it's going to go up, it's going to be doubled. Instead of 4, it's going to be doubled to 8. Instead of 9, it's going to be doubled up to 18, way up there somewhere. And there's my stretched graph. But that red curve does not yet have the shifts. So how do I include the shifts? I take we only have 1 in this case, but I take all those points and I move them all down 3. Right? So I'm going to move this one down 3. 1, 2, 3. 1, 2, 3. The vertex goes down 1, 2, 3. 1, 2, 3. 1, 2, 3. There would be my final curve, but it's kind of messy. You can see why it's nice to have different colors. So what if I just try to do it once? Well, I take my vertex and I move it down 3 because I know that's where it's going because the stretch and compression didn't change the vertex. And from there, I think about my pattern. But I'm going to multiply by 2. So instead I'm going up 2, 8, 18. So over 1 up 2. Over 2 up 8. So it's 3 and 5. And then 10 more, which will go off the graph. And there you go, I've graphed it. So this one, I sort of showed the transformations as I went. I graphed it 3 times. Base function, then I stretched it, then I shifted it. So that I could look at where every point goes. But once I get good and I know about the growth pattern and how the stretch or compression affects that, I can just graph it right in place.